Hello, and welcome to this short discussion on radiation exchange. We're going to take a look at a little bit more complex problems. And the question we have to answer is, when we have a multi-surface problem with lots of different surfaces, how do we evaluate the heat transfer rates and the temperatures? Because the interactions are very complex. So we're going to start simple. We assume that all the surfaces are black bodies, and then we look at this diagram and we can say this surface is surface I. This one is going to be J equals 1, J equals 2, J equals 3, and then so on, all the way around. When we've done that, we can look at these and say, okay, since they're black bodies, we don't have to worry about reflection. All the incoming radiation gets absorbed. So we can convert our radiosity into a black body emission. That's convenient because the black body emission only depends on temperature. Then from our discussion of view factors, we can use the summation rule and the reciprocity relation to find the view factors for the various surfaces here. And once we do that, we can find the value for the heat transfer from this surface to this surface and the radiation transfer from this surface to this surface, and also from here to here and from here to here. And we can do that for each of these networks. So we'll do it for J equals 1, 2, 3, 4, 5, 6, 7. And we'll get Qi to J for J equals 1 to 7 and Qj to I for J equals 1 to 7. And then we can get the net heat rate by summing over J, Q dot I to J, and Q dot Ji. This should be subtraction. Now, most surfaces are not going to be black bodies. We're going to need to account for reflection. In an enclosure, you might have multiple reflections. So we assume each surface is isothermal. We assume each surface has uniform radiosity and irradiation. Now, this may not be valid for all surfaces, and if it's not, what we'll have to do is break up the surface. So we'll have to break, say, this surface up into several chunks, and each part of the surface satisfies those assumptions, or at least comes close to satisfying those assumptions. We're also going to assume that the surfaces are opaque, diffuse, and gray. So this allows us to use Kirchhoff's law. Our objective here is either to find the radiative heat fluxes, that's if we already know the surface temperatures, or to find the surface temperatures if we already know some external conditions that's driving the heat transfer in this system. So if we apply Kirchhoff's law to our initial heat transfer rates, we can actually come up with a relationship between the black body emission, or the temperature of the surface, and the amount of radiation leaving the surface. And it depends on the emissivity, right? So what this does is gives us a surface resistance. This resistance represents the resistance that the surface has to releasing radiation. So it's our surface radiative resistance. Now, if a surface is very large, like an enclosure, we can say that the surface area is approximately infinite, or at least it's infinite compared to some smaller object in the enclosure. So if the surface area is infinite, then the surface resistance is 0. If we have a black body, the emissivity is 1. And in the numerator, we can see we have 1 minus emissivity, so that means the surface resistance is 0. So black bodies and cavities both have surface resistances of 0, and large surfaces can be treated like black bodies. Now, to demonstrate this a little bit better, we're going to look at an example of a radiation shield. So a radiation shield is a radiation network with 3 elements, but 2 of the elements don't communicate. We have communication from element 1 to element 3 and element 3 to element 2, but element 1 and element 2 don't communicate. So this is similar to our existing thermal circuits. So we have our surface resistances here, 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 and here, and then we have our geometric resistances here and here. Now, in this particular problem, all the areas are assumed infinite. So all of these areas are assumed infinite and can be canceled because they're all equal. And if we look at this, the view factor from 1 to 3 has to be 1. All the radiation leaving 1 has to go to 3. So these resistances can be reduced to 1s. They can be essentially canceled. So once we've done that, we now have an equation for the heat rate from 1 to 2 based on the sum of all of our thermal resistances. So here we have a 1 over epsilon minus epsilon over epsilon. So this becomes 1 over epsilon 1 minus 1. Here's a plus 1. So this plus 1 cancels with this, or this minus 1 cancels with this plus 1. And you see the same thing here. So what we end up with is this total thermal resistance. And you can see the radiation shield has added this part right here. If the surface has a very low emissivity, this term is going to be much bigger. So we want to have a low emissivity surface as our radiation shield, something like a highly polished metal where emissivity is like between 0.05 and 0.1. Now we can extend this idea to larger radiation networks to solve more complex heat transfer problems. Now in practice, this requires a computer because of the large number of equations to solve. However, for simple cases like a 3-element network, we can solve this by hand. Now, we have an equation for the heat transfer rate from I to J. We've already established that. But we need to have the irradiation of the surface, G. And we get that by summing over all of the different surfaces that are irradiating the surface I, summing over J. And we need our view factors and everything for that. So what this does is it shows us that there's an additional surface resistance. So we can convert this summation. We eliminate G by replacing it with the sum over the radiosities from J. And that gives us the total heat rate. But it shows us that there's an additional thermal resistance. So this is like a resistance due to the view factors, the geometry of the problem. So it's like a geometrical resistance between surface I and surface J. And then once we have that, we can equate the surface heat flux, the heat flux moving from emissivity or blackbody emission to radiosity is going to be equal to the total radiation heat leaving the surface through the radiosity balance. So this allows us to relate the radiosity balance between all those surface nodes, those J sub I nodes, with the temperature of each surface, rather than just the radiosity itself. So we go through this process for each network node. We write a system of linear equations that can be solved. All of the summations become an equation. And then we have this large thermal circuit with each pair represented by a network element. The driving potentials become the radiosity differences, and we can put this into a computer and solve it. Now we can also solve it directly, right? If we have an equation for each surface, that gives us a set of linear equations. So we can solve that directly by matrix inversion or something similar to that. It's not usually recommended for more than 4 surfaces because you end up with a pretty complex set of networks. And you may also need to iterate. If your surface tension or surface temperatures aren't known directly and you're solving for your surface temperatures, you're going to have to iterate your solution. So it can be very complex. Now, sometimes we can simplify this. If we neglect conduction and convection and we look at a steady state system, the net heat transfer is 0, and we call this a re-radiating surface. All the radiation that enters a surface also has to leave. So this implies that radiosity is completely independent from the surface emissivity. And that is important because it makes it much easier to find the surface temperature from the radiation exchange. We can find the radiation exchange first and then use that to get surface temperatures. Now it's also important to note that there's some limitations here because of the many assumptions we made. I mean, isothermal gray surfaces with uniform radiosity, and we also assume non-participating media, that the gas in the chamber is not absorbing or emitting radiation at all. So we have a lot of idealizations. However, these methods are very useful as first estimates, And in some simple cases, they'll be enough to make engineering decisions based on them. Now, you can also look in textbooks or specialized journals to find more advanced methods or more complex methods. We also are going to look a little bit at multimode heat transfer. If we have to include conduction and convection, that's going to make our calculations a lot more complicated. And the reason is because you have terms that are proportional to temperature to the fourth. Convection is proportional to temperature, and conduction is proportional to the temperature gradient. So you have this very complex nonlinear system. And a lot of the times this is going to require numerical iteration. So unless the surface temperature is known or the geometry is very simple, these programs can be very complex. If you have a simple geometry, then you can solve them by hand.